I think I stop at 8. Okay, so we are given the light frequency over here. We are given the wavelength. What we need to find is the velocity. Well, how do we do that? We take the wavelengths, we multiply by the frequency, we'll get the velocity of the speed of light in that material. Okay, that's V. What we need to find actually the refraction index, and refraction index, its definition is C divided by V in that material. Well, you can just now substitute. You found V, you know what C is, you can substitute and compute and get the final result. Alright, number 9 we solved in class. Please take a look at it again. And this is the solution I provide for you as well. And will be posted online, but again, we solved that in class. I'm not going to go through this once more. Number 10, this was one of these pre-class assignments, and it was also in the, I think in the post-class assignments, and it was, we solved similar problem in class, and one of these was also in your sample test. So I will refer you to the sample test solution. Okay, so essentially this is application of the Snell's law, which you can apply to each layer over here. And for the parallel surfaces like this, you can immediately derive that n1 times sine of theta 1 will be equals to n4 times sine of theta 4. Okay, so and from here you'll be able to solve for theta 4. It will be the inverse sine of that thing. Okay, so I'm solving for theta 4. And after that, you can substitute the numbers and find the final result. Okay, number 11, the coil of a generator has that many turns, cross-sectional area is given, it rotates with that frequency. It's an uniform magnetic field, we need to find RMS voltage. We had an equation for that, so let me first write all the unknowns and knowns. Okay, so what we know is A, F. Actually, for the equation we're going to use, we don't need the frequency, we need to have the angular frequency, which is 2 pi times F. You can compute already the number. We are given the magnetic field. We know that N here is 391. Next, we'll just use this equation for the average, for the RMS voltage, okay, RMS EMF, and compute the answer. Okay, pretty straightforward. Next problem, 12. Okay, for 12, I will let you first read this. Okay, we need to reach the half of the maximum value for the current. For the current in RL circuit, we have the following equation. It's going to reach eventually at very big large times. Once the switch is closed, it's going to reach a steady value, and this maximum steady value we know how to find, but we don't have to actually find it to solve this problem. So we know that the current has to, at this certain time, will reach 1/2 of its maximum value, so 1/2 of I0. So let's just substitute this fact into this equation over here. I substituted, I simplified, did pretty straightforward math. Okay, I will let you go through this by yourself. This is the answer I got. Okay, and here I need to remember that the time constant for RL circuit is given by L divided by R. You can now substitute the numbers. L is given, R is given, logarithm of 1/2. You can use your calculator, of course. You will get a positive result here because logarithm of 1/2 is negative and you have minus in front. Okay, but it will be time in seconds. And then compute, compare with the key. Okay, I will let you do that again. I think it's important for you to actually go through these problems by yourself as well. Okay, so 13. Okay, so what we are given here is that what we have here, the electric vector field is pointing in negative Z, so it means that it points into the page. I define the conventional axis over here. Okay, so the velocity is in negative x direction, and I need to find the direction of magnetic field. I use the right-hand rule to do that, right? So I will point my arm in the direction of the propagation. My then thumb is going to point in the direction of electric field, and I will curl or bend my fingers perpendicular to that, and I will define the direction of the magnetic field. So right hand rule, again, there is a file posted with the summary of all the right hand rules we had in this class, and you can probably also review that subject if you are not confident about it in your pre-class video. Fine, very good. We will find the direction. It will be positive y direction, so either this or this. Okay. Next, we need to compute. Okay, so we need to compute the magnitude of the magnetic field if we are given the magnitude of the electric field, and that's the relation between them. It's sort of between the magnetic field and the electric field in the electromagnetic wave. You take the electric field, you divide it by speed of light, and you'll get the final result. Substitute the numbers, use your calculator, but from what I see over here, so 4.7 divided by 3 is approximately 1 something, all right, 1.5. This is 45 divided by 3, yeah, so 1.5 times 10 to the negative 3. Okay, so and this is this answer. So even without using a calculator, I can do that math. Okay, and I have to remember that it's y direction as we discussed over here. Right? Let's move on. So 14 is a solution which is based on superposition principle, where we consider the magnetic field generated by the current I1, okay, thumb in direction of the current, finger curl in direction of the magnetic field, and you will be able to see that here it's point out, here it's points into the page, so that's B1, that's B1. Okay, so that's for magnetic field B1 generated by the current I1. Now what about the current I2? Again, we consider in separation from the rest of the wires. Again, use the right hand rule. Here it will go in B2, here it will go out B2, B2. Now let's join these two pictures together, okay, and just redraw what we learned. So B2 at this point is pointing out, B2, and B1 here is pointing in. Very good. So now we need to find this total magnetic field. So the distance, well, r away. So this distance r, and this is the same distance r. We know that I1 in terms of the magnitude equals to I2. This is I2, and therefore the magnetic fields at that point A, where we need to find this, in magnitude are the same. Okay, in magnitude they are the same. Well, you know the equation for the magnetic field, right? Look at this, magnetic field generated by the wire. But at that point, because the currents are the same, the distance to this point from both wires is the same. The magnetic field in magnitude is the same. Well, in magnitude it's one thing, but what about the direction? The direction, as you can see, between B2 and B1 is opposite. So when we find the actual total magnetic field, it's the vectorial sum of both of them, okay? But when you sum two vectors with the same magnitude but opposite in direction, you get 0, okay? That's 0, so answer is E. Number 15, I will let you read it. Yeah, it's application of one single equation, which is motional EMF. Okay, so for that we have the following equation. Motional EMF is B times L, the length of that bar or the length of whatever is moving, times velocity, times sine of the angle between the velocity and the magnetic field, and in this case 90 degrees. So the sine is 1. Okay, BLV, okay, L is given, B is given, V is given, substitute, compute, check with the key. Number 16. Okay, so here we have radio wave transmitted by a particular radio station with a given frequency. What is the wavelength of these radio waves? Well, we assume propagation in air or the same in vacuum, right? So, and for that, we have the following equation for the speed of light of propagation, and it is frequency times the wavelength. For this we can solve for the wavelengths. It's c divided by the frequency. Substitute, compute, compare with the key. Let's consider 17. I will let you read it. Yeah, so 17, so we're given a coil over here, we're given the current. So the current in this wire is going to stop. It's going to stop over a given period of time, it's 0.07. So if the current stops, right, then the magnetic field which will be produced by that current is decreasing. Let's remember that fact, it's decreasing in time. But let's define now the magnetic field actually of that current. I will do it by, no, let's just call this B right here. So this B I will call external. It's external from the standpoint of this coil, so this is magnetic field generated by that current. So use the right hand rule, you will discover that on this side of that wire, it points out of the page. On the other side of this wire, it points into the page. And specifically, I need to indicate where it's gonna point inside the coil. So it points into the page inside that coil. Very good. So now we know that the magnetic field is decreasing. If magnetic field decreases, then the magnetic flux decreases. If magnetic flux decreases, we can use Lenz's law to define the direction of the induced magnetic field induced by the coil. And it will have, because of the decreasing flux, make sure that you understand this rule, decreasing flux, it means that the magnetic field will have the same, induced magnetic field will have the same direction as the external one, okay? The same direction. We need to indicate that direction inside the loop, and this is what I've done. Inside the loop, it has the same direction as the external one for the decreasing flux. So now we need to find the current, the induced current in that coil, such that it would be able to generate this direction of the induced magnetic field, and you can use the right hand rule to convince yourself that this will be the direction. Again, I am expecting you to be very confident with this type of problems, and therefore I'm not going through them in the details. We've solved a lot of them. Okay, use the right hand rule to cross-check that this induced current has the right direction to produce this direction of the induced magnetic field inside that coil. Finally, you'll be able to see that it is clockwise. Okay, next, what is the EMF? Well, the EMF is given by the change of the flux divided by time. Okay, this is written over here. That's the equation. So what does change? So we need to substitute the definition of the flux over here. The flux is given by the magnetic field times the area times the cosine of the angle between the normal to the this area, or to this coil, to the face of this coil, and this angle between the normal and the magnetic field. Okay, so the only thing which changes here is the magnetic field, because the area of that coil stays the same and the angle doesn't change. As a matter of fact, the angle here will be just 1, because the angle between the normal and the magnetic field is 0, so that will be just 1. Okay, substitute over here what we know. The area is given, magnetic field changes. How does it change? Well, it changed from 8.3 Tesla, 8.7 times 10 to the negative 3 Tesla, okay, to 0. Why does it change to 0? Because this current which was generating this magnetic field goes to 0, right? It stops. It means it goes to 0, then the magnetic field will also go to 0. Okay, it stops over this period of time. This period of time it's given, substitute, compute, get the final result. Check with the key. All right, so this one over here, one has to remember the following fact, that you have to measure all these angles of reflection from the normal. So this angle of reflection will be equal to this angle. Okay, the same about these two angles. Now you have to remember that you need to use the fact that this triangle, the sum of the triangle of the angles equals to 180 degrees, and then very simple math will bring you to the answer. I'm not gonna walk you through that. I will just let you solve it by yourself. I also wrote the solution over here, so you can cross-check the solution with mine. Yeah. And of course, cross-check it with the key. I didn't, so. Okay, 19. I think this one we solved in class, but let me go through this. So what is happening here? So that that magnet is moved toward the coil, toward the coil. Okay, if it moves toward the coil, the magnitude of the magnetic field is going to, inside the coil, is going to increase. If the magnitude of the magnetic field increases, we will use the Lenz's law in a little bit. It will correspond to the increase in flux. Okay, the first thing first, we need to define the direction of the magnetic field generated by that magnet. Well, we know it points from north to south. Here I indicated that, and specifically for me to apply the Lenz's law, I have to indicate the direction of the external magnetic field inside that coil. Okay, be external, inside that coil will be to the right, Okay, the magnet is moved closer towards that coil. It means that it will result in increasing magnetic flux. Okay, if the magnetic flux increases using Lenz's law, we know that the induced magnetic field has to be opposite to the external one. So that's the direction of the external. Then it means the induced will have opposite direction. The next step is what current, in what direction the current should be to generate this magnetic field. Okay, let me look on this picture from this side. Okay, I'm looking at it from this side. So this is my eye, I'm looking from this side. Okay, from this side, what I see is the following, that B induced inside that coil points into the plane. Okay, this is B induced. So what current, direction of the current should I have to have this B induced? Well, as far as I can see, it's that. As a matter of fact, it's very similar to this problem, right? In terms of the direction of the magnetic field. Anyway, so B induced goes in, so that means that what current should it be? Well, that direction. So don't remember that we have to indicate the induced magnetic field inside the coil. Would you put it outside of the coil, you'll get the wrong result. It's not the right thing to do. Okay, the induced magnetic field has to be indicated inside that coil, the direction of it. Okay, so and the corresponding current, right-hand rule. Thumb in direction of the current and cross-check. So you have to point your thumb in both directions to cross-check which current will actually result in this direction of the magnetic field. You've done this again many times in the class. I'm not going to go through this in details. Again, I can't really show you in this video when I'm recording it on the page. But if you have questions about this, please do not hesitate to approach me, and I will demonstrate you this right-hand rule in person, okay? Or on Zoom. Very good. So next step is, well, we know that the EMF which will be generated by this problem is given by a number of coils times the change of the flux divided by the delta T, the time over which this change occurs. The flux changing only because the magnetic field is changing. We know how the magnetic field is changing. It changes in the following way. We know number of turns. We know the area. Remember that the area has to be written in SI units. Okay, and we know the time. Substitute, compute, get the final result. Cross-check it with the key. Yeah, so this one we have solved again multiple times in the previous exam. So I'm not going to go through that. Right-hand rule, and make sure you understand. If you don't understand this, please approach me. We'll discuss this in person. All right. Thank you.